Good day, grade 10s. How are you guys doing? It's time for physics. It's time for physics. Today is lesson number 5. Lesson number 5, and we're going to be looking at the very simple concept of mass and weight. Mass and weight. But before we go into what we're going to be doing today, just have to remember that the previous lesson, lesson number 3 and lesson number 4, we were looking at the concept of momentum. We were looking at the concept of momentum, and then we went on to look at the law of conservation of momentum. And we did several calculations on that, and I hope that you managed to proceed and do even your own calculations so that you are now very familiar with how to calculate momentum and how to observe when momentum has been conserved or when kinetic energy has been conserved. Okay, but today we are now moving on to a very familiar topic on mass and weight. We did this topic when we were in grade 9, right? And when we were in grade 8, we have basically done this several times now, but we're just going to do it again. Okay, so our objectives for this lesson are that by the end of the lesson, we must be able to define the term mass, okay, which by now you should already be able to do. But then we will just give the definition of mass again. We will also be able to define what gravitational field strength is, okay, in relation to the concept of weight. Okay, gravitational field strength. To describe qualitatively the motion of bodies falling in uniform gravitational fields. So I think that will probably be the slightly new area that we're going to touch on in this lesson. This is the new ground where you are describing qualitatively the motion of falling bodies as they fall from the sky to the ground. Right, so that is what we will look at, and also just basically how to use the equation for determining weight or force as being mass multiplied by the gravitational field strength. Right, so these are our objectives for today's lesson. Please look at the objectives, compose yourself. Make sure that you have your textbook with you, make sure that you have the notes with you, and that you are able to understand these very simple concepts that we're going to be dealing with. So just take a few seconds, half a minute, to just look at the objectives. Okay, so welcome back, guys. Right, so on the board I have put some descriptions of the term mass and descriptions of the term weight. Okay, so we'll find that mass basically refers to the amount of matter that is in an object. So we know that objects are composed of atoms. All matter is basically composed of atoms, right? All objects that we see, whether it's the desk or if it's the table or it's the chair that you're sitting on or the bed that you're lying on, all of those things are composed basically made of matter, and that matter is made of atoms. And we are saying mass is the amount of matter that is then in that object, right? So if we have a table and then we want to measure the amount of matter that is in it, that's when we put that object on a scale, and then the scale then goes on to say this is 1 kg. The mass of this object is 1 kilogram. I'm sure I just went on to say 1 kilogram because we all know the unit of mass is the kilogram, right? This mass is the same everywhere. Okay, the mass is the same everywhere in the sense that your mass, if we are here on Earth, right? If my mass is, 70 something kilograms, or if your mass is 50 something kilograms, or your mass is 100 something kilograms, I don't know. Wherever you go, it is irrelevant where you are. Your mass will always be the same. Mass does not change. Okay? Mass does not change. It is the same everywhere that you go. Okay? So we should also know that we'll use this in relation to the concept of weight and observe how weight is actually dependent on where you are, right? So if I'm here on Earth, my mass is the same. If I'm on the moon, my mass is the same. It does not change, okay? Then we should also know that mass is a scalar quantity. Mass is a scalar quantity, okay? It only has magnitude. It does not have direction linked to it. Mass is a scalar quantity. Mass is a scalar quantity. Right. Now, if we look at weight, weight, on the other hand, is the pull of gravity on matter. Right? Gravitational pull on matter. So if you are now on this planet and you're on planet Earth, yes, this is planet Earth, the one that we're on. Your weight is dependent on the gravitational field strength of this planet. We know the concept of the force of gravity. The force of gravity is that force which is pulling us onto the ground, and which is why we are not just floating off. I'm sure we have talked about this before, right? So weight now is a concept of the matter that is in the object, but also in relation to the pull of gravity on whichever body that you find yourself on. By body, I'm referring to a planetary body. Okay? To say if you're on Earth, you have a certain weight. If you're on the moon, because the gravity of the gravitational pull or the gravitational field strength of the moon is different from the gravitational field strength of the Earth, you will find that your weight is less when you're on the moon as compared to when you're on the Earth. And then if you were on Jupiter, let's take it for example, your weight would actually be 2.5 times greater than what it is on this planet, the planet Earth. So I hope we understand. It's a very simple concept that weight is dependent on the gravitational field strength of the planetary body that you're on. So weight is not the same everywhere. Weight differs depending on the gravitational field strength. Right, so for our purposes here, I said in this lesson, or for now, we will take G just simply as being 10 meters per second squared. The gravitational pull. Right, the gravitational pull, to say if an object is falling, right, what is the gravitational pull here on the planet Earth? We will take it as 10 meters per second squared. Some will say, oh, what about 9.8? No, for now, let's just use 10 meters per second squared. So that's a very simple concept. The other issue is that weight is a vector quantity. Weight is a vector quantity in the sense that it has both size, magnitude, and direction. Right? It has both magnitude and direction, because if you are being pulled downwards, then you definitely have a certain direction in which you are moving. Okay? And then the size of the object in relation to the matter that is in the object. All these objects have matter, right? But in the other case, we say we have mass when we don't include the gravitational pull. The moment we include the gravitational pull, then we talk about weight. Okay? So just take a few minutes just to absorb that material. Just absorb the material. It's very simple material, but allow yourself to understand it. Okay? Just take 1 minute to do that. Just go through the few points again. Look at the PDF. It has much more elaborated notes. Okay. So now, if we are still here, we are now looking at the relationship between mass and weight. Mass and weight, because obviously these two aspects are very close to each other and they are related. So that is the relationship that we now want to see. How exactly do you then have one being changed into the other? How do you have mass being changed to weight, or how do you have weight being changed to mass? What is the relationship between the two? And we have here a simple formula that says weight is equals to mass multiplied by the gravitational field strength. weight is equals to mass multiplied by the gravitational field strength. The beauty of it is that the moment that you have the equation weight is equals to mass times gravitational field strength, it means that you can then substitute it for mass for you to find mass being equal to 1. Let me just do it. So if we were to say we want to find mass, it would mean that weight divided by gravitational field strength would give us the mass, right? So you can then substitute it in any way that you want to find, either for the weight, for the mass, or if you're actually given both and then you want to find the gravitational field strength, you can actually also do that, right? Substitution, making something the subject of the formula. If you want to find mass from that equation, you can also do that, right? If you are given force and gravity, you can find mass. If you are given mass and gravity, you can find force, right? If you are given mass and force, you can actually tell what the gravity is, or the gravitational field strength is, or what the acceleration of a body is. Okay, so if you are given the mass of a body and you are given the force which is acting on it, you can actually get to say this body is then being pulled down by a gravitational field strength of X or Y, right? Using substitution, or making whichever value you want to find subject of the formula, right? So we are then going to use this equation, right, just to do a few simple calculations, right? To do a few simple calculations. The first one that I will do, that you guys will do, is I'm going to read it out. I'm going to read it out, and then you guys can attempt it where you are. But then I will also write the response or the answer for that question for you on the board. Okay, then I'll give you other questions which you will do by yourself. Okay, that is later, or for your assignment, for your homework. Okay, this homework, let's say today is the 11th. I think today is the 11th. Yes, today is the 11th. I will give you this work tomorrow, which is the 12th. The work will be due on the 15th. The work will be due on the 15th at 5 p.m. So that's it about the work. I'll give you work. The work will be due. I will expect it in my email address on the 15th at 5 p.m. Okay, cool. Right. So let me read a question for you from your living physics. It says, a man stands on a scale on the moon. A man stands on a scale on the moon. The scale shows a reading of 180 newtons. The scale shows a reading of 180 newtons. Gravitational acceleration on the moon is 1.62 newtons per kg. Okay? Gravitational acceleration on the moon is 1.62 newtons per kg. Calculate the mass of the man when he's on the moon. Determine his mass if he is on the planet Earth. Okay, so gravitational acceleration on the moon is 1.62 newtons per kg. Number one, calculate the mass of the man when he's on the moon. And number two, determine the mass of the man if you were on the planet Earth, right? If you were here on the planet Earth. So I'll give you 4 minutes for that. Don't even rush yourself. Just do the calculation. Okay, so I hope you guys were able to do this simple calculation where the man was standing on a scale on the moon and his weight on the moon was 180 newtons, right? And then you define the mass of this man, right? So we would say for finding the mass, right? For finding the mass, we then went on to say, let me see if I can point at it properly. So if you're finding the mass and then you are looking at weight is equal to mg, m is equal to, when you substitute for m, right? I'm trying to point at it, yes, there, m then is equal to w over g, right? Which means that m then became 180 newtons, which is the weight, divided by g, which is 1.62 newtons per kg, to give you 111.11 kgs. So the main concept there is just where you make the mass the subject of the formula, and then you have your mass now being equal to weight over gravitation or field strength. So that is the mass. It's a very simple calculation. Then the second question is almost like a trick question in the sense that the answer is already given. What is the mass of the man on the earth? Because you already know the mass of the man on the moon, it means that you also know the mass of the man on the earth, on the planet Earth. You also know his mass, whether he's on Saturn or on Jupiter or on Venus. It doesn't matter because mass is the same everywhere. Mass is the same everywhere. So his mass comes out again as being equal to 111 kilograms. That is his mass. Okay? So that is the simple relationship, okay, of calculating or finding what, if you are given weight, how you find mass. If you are given mass, how you find weight. And if you are given mass at a certain place, you know that it's the same mass. Okay? So it's a very, very simple concept. Okay, so now let's just look now at the concept of falling bodies. Right, so we also said we want to look at the concept of falling bodies in a certain gravitational field strength. Right, describe the motion of bodies falling in a uniform gravitational field strength, qualitatively. So if we have a body that is falling, let's say maybe someone jumps out of a plane, like in the Fast and the Furious, or or those crazy movies, someone jumps out of the plane, you're like, why is someone jumping out of a plane? But okay, they've jumped out of the plane. Now when they've jumped out of the plane, they are now a falling body. And there are two forces that act on this body as it is falling from the plane. Right? One, there is the weight of the body. Okay? There is the weight of the body, and also there is something that we call air resistance. So as you are falling now, as the individual or whatever body that has been thrown out of the plane, okay, let's say it's a box, let's not say it's a person, let's say it's a box, a big box, heavy box, has been thrown out of what? Out of the plane. The weight of the box is then going to propel it to move downwards. Okay, because remember, it's in a place that has a uniform gravitational field strength, so it is going to be pulled downwards. It's going to be pulled downwards. So as it is being pulled downwards, it is now accelerating. It keeps on speeding up, moves faster and faster, because remember, acceleration, we say you are falling at a speed of 10 meters per second squared. Meters per second squared. It continues to increase as the object falls, right? So if you were to check the velocity of that body, right, the velocity of that body as it is falling, the velocity is increasing. It's moving faster and faster and faster, right? But then as it is moving like that, then we also have a second force that acts on the body, and this is known as air resistance. Okay, so you can't just fall down as if you are moving through a blank space, a vacuum where there is nothing. Because there are particles that are there in space, it means that there's going to be resistance that's going to resist your downward fall. Okay, so it's effectively almost going to catch you, right? It's effectively going to catch you and prevent you from falling as quickly as you would if there was nothing in space. But we know that space is not a vacuum, right? If you're falling from the sky and you're falling downwards, there are a lot of particles that are there. So there is something that we call air resistance. So it resists the objects falling down. The motion of the object as it is falling down is resisted by the air resistance. And this air resistance depends on the speed at which the body is moving. The faster the body moves, the more the air resistance is. Okay, and also the surface area of the body, right? So if there's a greater surface area, then there's also going to be a greater air resistance, because now there's a bigger area for which the particles to catch this falling body. Why do we talk about this? We talk about this concept because we want to get to this issue of something known as terminal velocity, right? Terminal velocity. To say now that if the object is falling down, right, is being pulled down because of its weight, right? Because of its weight, and its weight is dependent on the gravitational field strength. The gravitational field strength is pulling down this object. It has a mass, right? It has a matter in it, and because there's a gravitational field strength, therefore it has weight, and that is why it is falling through space. But as it is falling through space, remember that there is also air resistance. So we are saying you would assume that the box would continue if the box was falling from the plane, right? That the speed of this object would continue to increase and increase and increase, right? But at some point, the air resistance is actually going to match, right? As the body falls, air resistance eventually equals the downward force, and the object stops accelerating. We didn't say it stops moving, it stops accelerating. So now if you're falling maybe at a speed of 100 meters per second, then you maintain a speed of 100 meters per second. And trust me, if you're going to fall from a plane at a speed of 100 meters per second, it's not going to end nicely for you. Whether you fall into the ocean or you fall onto the ground, it's not going to end nicely. So hopefully you will have a parachute, right? Then when you take out a parachute, then you increase your surface area, right? That's the whole concept of parachutes, by the way. When you take out the parachute has a much larger surface area. So therefore the air resistance, the particles that are now resisting your downward fall, have a bigger area to actually be captured on. So you will find that immediately the air resistance increases, right? The air resistance increases and it almost supersedes your weight. That's the whole concept of a parachute as you're falling down from a plane. So if you jump from a plane, make sure you have a parachute. Don't just jump from the plane. So the parachute, when you release it, then your downward motion then reduces significantly. Okay, it reduces significantly. But if you're thinking of the box, if you've ever seen medical packages being delivered to third world countries, this one is a second world country, right? It's a first world country or something like that. If you've seen medical aid packages being sent, or food packages, or even when people are at war and then they are having these boxes with machinery in them, then when they're being delivered, they always have these little parachutes, right, that eject from them, and they slow them down and they land nicely. If the boxes were just to fall like that from the sky to the ground, it's just bam, and they're crushed and they disintegrate, and it's a waste of time. So you put parachutes in there so that you can counter the downward motion of the falling body. The downward motion of the falling body is as a result of the weight of the body. The weight of the body, all right? But it's also being countered by, so the downward force, the weight is pulling it down, and the gravitational field is pulling it down, but the air resistance is now countering it. So what you do is that when you get to a point when we say terminal velocity is the point where the air resistance has matched the weight of this falling body. And when they match and when they are equal, the velocity now is the same. This body is now falling at an equal velocity. If it's 50 meters per second, or if it's 155 meters per second, whatever velocity it is falling at is the same, right? So that's the whole concept of terminal velocity. Falling bodies being acted upon by two forces, the weight of the body and the air resistance. Okay? And then if you want to increase air resistance, increase the surface area of the body. That's how the whole concept of parachutes work, right? So when you release the parachute, you increase your surface area, or not necessarily your surface area of the body, but of you, because the parachute is also attached to you. So you, as the falling body, have now increased your surface area significantly, and it reduces your velocity downward, and then you're able to land safely and come back to school and say, guys, I went on a trip, and then we went skydiving, and then all of that stuff. Hopefully you tell us your stories when you come back, right? Cool. Okay, so we have looked at lesson 5, mass and weight. We are able to define mass. We know what a gravitational field strength is now. If you still don't know, just play the video again. Falling bodies, the concept of terminal velocity, very simple, by the time we got to it, we found that it's actually very simple. Okay, so please read, watch the video again, read the PDF. I'm going to, there is work on the PDF, and like I said, that work will be submitted on the 15th at 5 p.m. Okay, so as always, guys, you've been amazing. This is your teacher, Marshall A.C. Candiado. Thank you very much.